Welcome to the first video about systems of linear equations. In this video we're going to do three things. We're going to review basic systems of equations, we're going to generalize those systems to larger systems, and then we're going to solve those general systems of equations. So first let's review a simple example from basic algebra, something like this: 2x plus y equals 8 and minus x plus y equals -1. From basic algebra, we know a few different ways to solve this system of equations. One way is graphically. So if I graph this first equation, 2x plus y equals 8, I'd get this red line here. If I graph the second one, minus x plus y equals -1, I'd get this blue line. And I can see here on the graph, it looks like those lines intersect at about 3, 2, so 3 on the x-axis, 2 on the y-axis. So it looks like the intersection is the point 3, 2. And then if we think that's the solution, we can check. We let x equals 3 and y equals 2, and we plug those values into the system. We plug in a 3 for x in both equations, and we plug in a 2 for y, and we can see that 2 times 3 plus 2 is 8, so that equation is satisfied, and minus 3 plus 2 is -1, so that equation is satisfied. Another way that we can solve a system like this is by elimination, which is sometimes called addition. If I take the system and multiply the second equation by -1 on both sides, then I get an equivalent system. I can write that down here. 2x plus y equals 8, and then x minus y equals 1, and I can add those together, and then I can see that the y and the -y are going to add up to 0, so I eliminate that variable. That's where the name comes from. So I get 3x equals 9, and then divide both sides by 3, and x equals 3. Then I can plug this value for x into either one of the original equations. Let's plug it into the second one, and I can get minus x plus y equals -1, so y equals 3 minus 1, or 2. And of course we get the same answer, and our solution set is the set containing the point 3, 2. Alright, that works great for small little systems like this with 2 equations and 2 variables. Now we're going to generalize this technique for much larger systems. In linear algebra, we often have systems with many hundreds or even thousands of equations and variables. The first step in generalizing a small system to a larger one is to rewrite the variables. If I only have a couple of variables, I can use different letters like x and y. But if I have dozens or hundreds of variables, I'll run out of letters. So we pick one letter, often x, and then just use subscripts for each variable. So I'll have x1, x2, and I can go up to x3, x4, as many as I need. So I rewrote my original system and replaced x with x1 and y with x2. Now I'm going to take advantage of the format of this equation to simplify what I'm writing down to make it easier to manipulate. Notice that the x1s are lined up in a column here, and the x2s are lined up in a column, and then these plus signs are lined up in a column, and so are the equal signs. And if I always write plus signs for all my terms, which I could do if I have a negative, I could write plus a minus, and always put the equal signs in this position so that their constant terms are on the right, and there's only one term on the right, and the equal signs are right before that, then I can eliminate writing these things. I don't have to write x1 and the pluses and the x2 and the equal signs. I can just write something like this. All I really need to know are what are the coefficients. In other words, I can use this thing, which is called an augmented matrix, where each row represents an equation. I know the last column of this matrix represents the constant term, so I can imagine the equal signs in between here. And I know that these columns represent the variables, so if there are two columns, there must be x1 and x2. If we had a third column in here before this last one, that would mean, oh, there's three variables, so there must be an x3. And in between these columns, I'm going to imagine plus signs. So we've kind of taken out some of the unnecessary or redundant information in this format of writing the system and just put in here what's really essential, which is really just these coefficients here and these constant terms. All right, so how can we use this augmented matrix? Well, we need a few definitions first before we can see how this is useful. So what we're going to do is called row reducing the augmented matrix. Row reducing means we're going to apply these elementary row operations to the matrix. These are based on the properties of algebra that allow us to solve equations, like multiplying an equation by the same number on both sides. If you go through and read these, you can see how these correspond to things that you can do to solve equations. We say two matrices are row equivalent if one can be obtained from the other by a sequence of elementary row operations, and we write A is row equivalent to B. The tilde symbol means row equivalent. So if I take a matrix A and perform some sequence of these types of row operations to get another matrix B, those two matrices are row equivalent, and we would write A tilde B, which means A is row equivalent to B. The goal is to get this matrix B into what we call reduced row echelon form. This is the definition of it. It's kind of technical. You can read through it and study examples in the book. We'll do an example to show you how it works. And then once we get it into this reduced row echelon form, which we often call RREF for short, then that allows us to see the solution of the system more easily, and that is based on this theorem, which says that the reduced row echelon form of every matrix is unique. This will be handy because then we'll know that when we row reduce our matrix, there's only one possible answer that we could get. Okay, so let's go back to our augmented matrix and let's row reduce it and see what we get. Here's our augmented matrix from before. And this notation means I'm going to multiply row 2 by 1 and add it to row 1, and then I'm going to replace row 1. Now how do I know that I'm going to replace row 1? It says 1 R2 plus R1, but it doesn't say replace row 1. Well, if we go back here and look at the elementary row operations, we can see that the first one says replace one row by the sum of itself and a multiple of another row. You can also interchange two rows or just multiply all entries in a row by a non-zero constant. This one, though, number 1, is the one we do most often. And notice what it says. It says replace one row by the sum of itself and a multiple of another row. So you multiply one row by a number, and then you don't multiply the other row. So one row gets replaced by the sum of itself, not itself multiplied by anything, just by itself, and then you multiply the other row. So whenever you see an expression like 1R2 plus R1, well, R2 is getting multiplied by something, and R1 is not. So this expression is going to replace the row that's not getting multiplied, in this case, R1. And that's why I've written 1R2, when really I don't need to. I could just write R1 plus R2. But if neither row is multiplied by anything, I don't know which one's getting replaced. So we write 1R2 plus R1, and that tells me, okay, multiply row 2 by 1, add it to row 1, and then replace row 1 with that sum. So that's what we do. We're basically just going to add these two rows together, and then we're going to replace row 1, because it's not getting multiplied, by the sum. Whenever I do this, I actually do it backwards. I look and see, well, which row is getting replaced? Row 1 in this case. That means row 2 is not getting replaced, and I just copy and paste that one over. That helps me avoid making little mistakes. So I see, okay, row 1's getting replaced, row 2 is not, so I'm going to just copy and paste row 2. And then what's the new row 1 going to be? Well, I just add these together, and I get the numbers in row 1. the new row 1. Okay, and then we're going to do almost the same thing. We're going to multiply row 1 by 1 and add it to row 2. So we're just adding these numbers together again, but this time we're going to replace row 2. So row 1 stays the same. I add 1 plus negative 1, 2 plus 1, 7 plus negative 1 to get my new row 2. And then I'm going to do minus 2/3 row 2 plus row 1, and row 1's not getting multiplied, so it's the one that's going to get replaced. Row 2 stays the same, so 0, 3, 6 stays 0, 3, 6. And then I'm going to multiply this second row by a minus 2/3. And if you notice what's going to happen, when I multiply the 3 by minus 2/3, it's going to turn into a negative 2. And that's what I want, because then when I add these two together, I'm going to get 2 plus a negative 2. All right, so when I do that, then my new row 1 will be 1, 0, 2 plus negative 2, and then 3. So minus 2/3 times 6, well, let's see, 3 goes into 6 twice, so that's going to be a minus 4, plus 7, what's going to give me 3. All right, and then finally, I'm going to do 1/3 times row 2. This is the first time we've done this third row operation, multiply all entries in a row by a non-zero constant. So you're not really replacing anything, you're just scaling this last row by 1/3. So just divide every number here by 3 to get 0, 1, 2. Now, I didn't say why I was doing these particular row operations, but this is why. Now at the end you can see, notice this form here. This is in the reduced row echelon form. So I didn't go through all this in detail in this video, but if you look through this and compare these 5 conditions to this matrix, you'll see, yep, this satisfies all 5 conditions. And when we see how easy it is to observe the solution set, you'll understand why those 5 conditions are what they are. What I wanted to do, starting here, is get the matrix into this pattern where I have a 1 here and a 0 underneath. And then somewhere to the right, if it's a longer matrix, it might be, not the second column, could be the third or fourth column, but somewhere to the right of that, I'm going to have another column with a 1 in it and zeros above and below if there were more rows underneath. And then farther on the right, I'm going to have maybe some columns that don't have zeros or ones in them. But basically, you're going for this stair-step pattern of ones and zeros everywhere else. That's kind of what this reduced row echelon form is in a nutshell. Okay, so how is this easy? How is this form of the matrix easier than this form to observe the solution? Well, now we write down the corresponding system. Remember, each row represents an equation, and the first column represents the x1 variable, the second column represents the x2 variable, and the third column is the constant term. So this first row says 1x1 plus 0x2 equals 3. So there's my first equation. The second row says 0x1 plus 1x2 equals 2. So there's my second equation. Well, now when I'm looking at this, that's so simple, I can just write down x1 is 3, x2 is 2. So there's my solution set, the set that contains the point 3, 2. At least it seems like that's the solution set, but there are some questions that remain unanswered. How do we know for sure that it is? How do we know that it's the only solution set? Is it the only point in the solution set? Could there be other points in the solution set? Do we know for sure that there are no other points? So we have a little bit more work to do to generalize this, to answer all these questions. And we'll do that next, and then we'll do a couple more examples and we'll be done. Okay, to summarize, we've been generalizing the elimination technique that we did here to solve the system, where we did basic algebra to come up with the solution set. In order to completely generalize that, we need to define some things and label some things, and even look at a theorem or two. So first we're going to talk about equivalent systems. We say that two systems are equivalent if they have the same solution set. So that's what equivalent means when we're talking about systems, same solution set. And then our first theorem here says that if A and B are the augmented matrices of two different systems, and if their augmented matrices are row equivalent, then the two systems are equivalent. So you can think of it as row equivalent augmented matrices correspond to equivalent systems. Okay, then some other things. We're going to talk about the augmented matrices themselves. We're going to define a pivot position as a location in the matrix that corresponds to a leading one in the reduced echelon form of the matrix. So if we look at our augmented matrix that we got before, this was the reduced echelon form, and the leading ones were here and here. A leading one is the first non-zero entry that you come to as you read across each row from left to right. So the very first number I come to in the first row is non-zero, so there's my leading entry. And if the matrix is in reduced row echelon form, that leading entry will always be a 1. If I go down to the second row and I look across from left to right, that's a 0, so I keep going. Oh, there's the first non-zero number, and it's a 1, and that's a leading 1. And these are called pivot positions. Okay, and the columns that they're in are called pivot columns. So we could say these are my pivot columns. All right, then the next definition talks about dependent and independent variables. If a variable corresponds to a pivot column, it's dependent. If it corresponds to a non-pivot column, well, I have to be careful because this is not a variable column. If you remember, these are the constants. This would be the x1 column and the x2 column. And if there's a variable column that's not a pivot column, it's an independent variable, which we will usually call a free variable. So we could label these columns. This is the x1 column, the x2 column, and then these are the constants. So that's the constant column. Because every variable column here is a pivot column, these are both dependent variables, and there are no free variables in this particular system. So we could say x1 and x2 are dependent variables. And there are no free variables in this particular system. Some systems have them, some systems don't. Every system has at least one dependent variable. And then we come to the main theorem of this section. This is the Existence-Uniqueness theorem. It's kind of a strange name, but there are lots of these types of theorems in math and science and applications and engineering that are actually really important. They tell us not only that a solution exists, but also that it's unique. Oftentimes when we're trying to solve a practical problem, it's useful to know before we start solving it that a solution exists, and furthermore that the solution is unique. Lots of practical problems require unique solutions. If there's a solution but there's not a unique solution, and there are lots of possible solutions and we don't know which one we're going to get, when you turn the key in your car, maybe it'll turn on and fire up and run great, or maybe it will explode. So we want to have a unique solution to practical problems many times so that we can predict exactly what's going to happen. So this is a great and useful theorem. And it tells us when a linear system has a solution and what kind of a solution it has when it does. So we say that a linear system is consistent. We'll define this word formally later, but for now it just means it has a solution. And that happens when the rightmost column of the augmented matrix is not a pivot column. And then if it is consistent, then we can decide what kind of consistent system it is. It will either contain one unique solution if it has no free variables, or infinitely many solutions when there's at least one free variable. So it's kind of complicated. There's a lot in there. But as we go through the examples and apply this theorem, you'll see how it works. Okay, if we put all this together then, we can go back and look at our problem that we solved. We found the solution set to be the set containing 3, 2. But what about these questions? Well, those are answered here. First of all, we know that the solution set for the system corresponding to the row-reduced augmented matrix is the same as the solution set of the original system. That was the theorem that we just saw. And then In addition, because the augmented matrix had two pivot columns, there's no free variables. And so by this theorem 1.3, we know that there's a unique solution. And we found one, 3, 2, so that must be it. That must be the only one. Okay, let's put this all together now and solve a few more examples and see how this works. Here's another system. This time I've got three variables, x1, x2, and x3, and I've got three different equations. Notice in the third equation there's no x1 term, but we left a little bit of space here so that we can easily identify the coefficients of the different variables. In other words, each of the variables in the equations are lined up in columns so that this looks very much like what my augmented matrix is going to look like. It's nice that the system is given to us in this format. If it's not, we can always rearrange the terms and put all the x1 terms first, and then the x2 terms, and then the x3 terms, and then put the constant terms on the right side. All right, so I can just read the augmented matrix right off of the system. I'll go down each column. So the x1 column is going to be 1x1, minus 4x1, 0x1. So 1 minus 4, 0. There's my first column. The x2 column will be 3 minus 9 minus 3. The x3 column will be 1, 2 minus 6. And the constant column 1, negative 1, 3. Remember, this tilde symbol means row equivalent. And I've skipped the steps of row reducing this matrix. I did this on a computer, and there's a separate video that explains how to do that. It's very straightforward. You can use a calculator or a computer. You put this matrix in and then hit the button, and it reduces the matrix to reduced row echelon form, and here's our result. So the first thing we want to do after we row reduce the matrix is identify the pivots. Okay, there's my two pivots. And using the existence-uniqueness theorem, since there's not a pivot in the last column, the system is consistent. That means it has a solution, or more formally, the solution set is not empty. So there are going to be some values of x1, x2, and x3 that I can plug into all three equations to satisfy all three equations at the same time. Okay, great. It also tells me that x1 and x2 are my dependent variables. And in this case, since x3 does not correspond to a pivot, it's not a pivot column, x3 is free. So we can label these two as my dependent variables, and x3 is free. And we'll see how that works in a minute. Remember, the last column is always your constants. So there's no x4 here. This is not the x4 column. This column came from this column, which corresponded to the constants on the right hand of the equal signs. All right, then we write down the equivalent system, or the system that corresponds to this row reduced form of the matrix. Notice the last row is all zeros. So this is kind of weird. It tells me 0x1 plus 0x2 plus 0x3 equals 0. In other words, 0 equals 0, but I already knew that, so it's not very helpful. I'm not going to bother writing that down. I'm just going to write down these two equations, or the equations corresponding to these two rows. So the first row says 1x1 plus 0x2 minus 5x3 equals minus 2. So I leave off the 0 term and just write x1 minus 5x3 equals minus 2. The second row says x2 plus 2x3 equals 1. And then I want to solve for the dependent variables in terms of the free variables. If there are no free variables, then you get a unique solution like we did in the previous example, and the dependent variables will just be solved in terms of the constants. So we'd have, just a single dependent variable equals a number, and another dependent variable equals another number. But in this case, since x3 is free, we're going to solve for each of the dependent variables that we identified up here in terms of the free variable. So just put those free variable terms on the other side, and then I'm going to write my system like this. And then I'm pretty much ready to write down the solution set. the solution set is all of the ordered triples, in this case x1, comma, x2, comma, x3, that satisfy this system of equations. In other words, the x1 component of this ordered triple, or point, if you will, has to equal 5 times this number minus 2. And then the second component of the point, x2, has to equal minus 2 times this number plus 1. And then the third component can be anything. It's just this number, just x3. So we can write it out in set notation like this. The solution set is the set. The curly brackets mean a set. And then the parentheses describe the point. And the first coordinate is 5x3 minus 2. The second coordinate minus 2x3 plus 1. And the third coordinate is just x3. The line here is read such that, that's set notation, and this funny looking E thing is the Greek letter epsilon, and it's read is in, and that capital C in the strange font is the set of complex numbers. So there's a lot of new symbols in this class. In the beginning they're all different looking, but eventually you'll learn what they are and we don't have to take so much time deciphering it all. So we would say this is the set of these points such that x3 is in C, which just means x3 can be any complex number. And in this class we're generally going to be working with complex numbers, not just real numbers. All right, here's another example. This is another system that has 3 equations and 3 variables. And it's just a coincidence that I'm doing 3x3 systems, as we would call these. They're a little bit bigger than a 2x2, but not too much bigger. So we're kind of easing into larger systems. You can have any number of equations and any number of variables. So I could have 7 equations and 4 variables, or 18 variables and 5 equations, or whatever. Notice that in this first equation there's no x2 term, so I've left some space here between the x1 and x3 term for the x2 term. And in the beginning, if you want to, you can even write in 0 x2 there plus 3x3, just kind of as a placeholder, so that you can just read the columns right off of your system. So when I write down the augmented matrix, I'll get 2, 4, 8, 0, minus 3, minus 9, 3, 7, 15, 3, 5, 10. There it is. Row reduce it on the computer. This is what I get. Got some fractions here. That's fine. And just as we did before, we're going to identify the pivots. And in this case, we get a pivot in the last column. So remember, the pivot is a leading 1. And in this last row, if I go across from left to right, it's all zeros until I get to this number. And that is not a 0, it's a 1. So there's my pivot. Okay. Easy enough to identify. And from the existence-uniqueness theorem, we know that this system is inconsistent and the solution set is empty. Let's look at what this last equation tells us. In the previous example, the last equation said 0 equals 0. Okay, that was not very useful. Well, what does this last row tell us? It says 0x1 plus 0x2 plus 0x3 equals 1. Well, that last row then can be simplified to 0 equals 1. And this equation doesn't depend on the variables. So I can pick any variables, any numbers for these variables that I want, and I'm never going to make 0 equal 1. And that's why we say this system is inconsistent. So we sometimes say that it has no solution. What we really mean is there are no numbers we can plug in for x1, x2, and x3. Every system has a solution. There's always a solution set, but in this case it's the empty set. And the empty set here is this symbol that looks like a 0 with a slash through it. You can also write the empty set as a pair of set brackets like this with nothing in there. Be careful though, the empty set is not this. That's not the empty set. so don't make that mistake. This thing inside there, that's the set that contains the empty set, which is not empty. So if we think of the empty set like an empty backpack, and this is another empty backpack, these two mean the same thing, they're just different symbols for the empty set. If I put this empty set inside this empty set, well, this one's not empty anymore. These curly brackets are like a backpack that contains an empty backpack. So this outside backpack is no longer empty. All right, but notice we didn't have to do anything else once we found a pivot in the last column. Bam, we're done. We can say the system is inconsistent and the solution set is always the empty set. Doesn't matter how many variables there are or how many equations there are. If there's a pivot anywhere in the last column, this is your answer. The solution set is the empty set. Okay, let's do one more with a few more variables. So we're going to get more free variables, and you'll see how that can happen or what that looks like. In this system, we've got 2 equations, but 4 variables. So we're going to do the same thing we did before. We're going to write down the augmented matrix, and we can just observe the augmented matrix from the coefficients. In this case, each equation has a non-zero term for each variable. This makes it a little easier. So just going across the system for 3, 12, 9, minus 7, minus 5, columns here, minus 20, minus 28, 22, 30. We'll reduce it on your calculator or the computer and identify your pivots. There's a pivot, there's a pivot. So I only have 2 pivots in this augmented matrix. If I identify the columns that correspond to each variable, I've got my x1 column, x2, x3, x4, and the constant column. I can see that x1 and x3 correspond to my pivot columns, so those are my dependent variables, and x2 and x4 are free. So I can write x1 and x3 are dependent, and x2 and x4 are free. Free means they can take on any values. Dependent means the values of x1 and x3 will depend on the values that we pick for x2 and x4. All right, same thing as before. We write down the equivalent system. So each row of the augmented matrix corresponds to an equation. We write those down. We solve for the dependent variables in terms of the free variables. So I'm going to take all the x2 and x4 terms in these equations over to the right side and solve one of the equations for x1 and the other one for x3. Okay? And then I write down the solution set. Now remember, since I've got 4 variables, my solution set is going to be points with 4 entries in them. So you could think of this as a point in 4-dimensional space. It's kind of hard to picture that maybe, but we use this in science and engineering all the time. General relativity is in 4-dimensional space, for example, space-time. Okay, so the first coordinate is going to be minus 3x2 plus 96x4 plus 100. So we got some bigger numbers here, but that's fine. So there's my first coordinate. Now notice x2 is just x2. Why? Because x2 is free. So each of the free variables just appears by itself in your point. And then x3 is going to be this expression, and then x4 is itself, and then such that x2 and x4 are in C. Notice we only refer to the free variables here. They can be any numbers in C, but then x1 and x3 are set. Once you pick x2 and x4, well, that determines x1 and x3. So there's our solution set. All right, so we reviewed basic systems, we generalized those basic systems, and then talked about how to solve those general systems. So at this point, you should be able to solve any size system with the help of a computer, probably to reduce the matrix, and write down the solution set.